There are a number of different ways to define solutions and how much solute is in a given solution. These are kind of complicated problems. They end up getting much more complex than what you may want them to be, but that's okay. Hang in there. It's okay if they're frustrating. Once you get through a few of them, you'll be okay. So let me go through some definitions here, and then I will sort of give you some pointers on this as well. Mass percent is the mass of the solute divided by the mass of the solution. So keep in mind, the mass of the solution is the mass of the solvent and the mass of the solute. So those two things have to be combined, right? Okay. So volume percent is the volume of solute divided by the volume of solution. Now, you would think that means that if you add 15 milliliters of this thing and 15 milliliters of this thing, so that'd be 30 milliliters. Please be aware that that is not necessarily the case, and you have to use special glassware to make sure that that is the case. Because the truth is that two different liquids or molecules, period, can kind of fit in between the molecules of the other one. So this could end up being 27, it could end up being 23. You have to figure that you have to be like either given that in a problem or you have to measure it yourself, okay? Mass volume percent is the mass of a solute, usually this is in grams, over volume of solution. Usually this is in milliliters, not always. For the purposes of my course, at least, it will be in milliliters, okay? And then molarity is the moles of the solute. This is the only one that deals with moles over the volume of solution. So here's what I'm going to suggest. When you approach problems like this, I first want you to think about, what am I looking for? Am I looking for stuff in grams? Am I looking for things in volume? What am I looking for? And just figure out what that is on top and what that is on bottom, and then put the two of them together. And in these cases, if it's a percent, times 100%. Okay? So figure out the unit that you need for each of those missing parts, and then just put it in this just like it was a formula. Okay? Okay. Now, there's a whole bunch of those types of problems that you'll see out there. One of a more complicated type of problem is also, seems easy, the equation for making dilutions of a given solution. Let me repeat that. To make a dilution of a solution, that sounds fun, right? You take something that's concentrated. You would take something that's concentrated, put a little bit of that into another flask, and then you dilute it with a solvent, such as water. Okay, it doesn't have to be water, but that's probably what you're most familiar with. So in this case, we just use a nice little equation. And as long as the units cancel out and they're the same on both sides, then it doesn't matter which of these definitions that you're looking at. Okay? So C1V1 equals C2V2. Concentration of the first thing times volume of the first thing is concentration of the second thing times volume of the second thing. Okay. Okay. This is something that I would have to give you an example for in a different video. So I'm just giving you that equation for now. Okay. Solutions are going to behave differently and than their given solvents. We call these colligative properties. Okay, so let's start with something called freezing point depression and boiling point elevation. When you have a mixture, you've got water, okay? Pure water, the boiling point is 100, the freezing point is 0. Now let's imagine putting some salt in that water. What ends up happening is when you start to boil the water, is the salt's basically pulling the water molecules down towards it, saying, I want you to stay with me, because they need that negative positive around them to keep them dissolved, right? So the boiling point goes up because it takes more energy now to get those water molecules up and out of solution and make them boil. On the opposite end, freezing point depression, Most of you probably know that when it's cold outside and you've got frozen ice out there, you can go and throw some salt on that and it'll make it go to a liquid. The reason why is sort of the same. Because once you start to put the salt on there, it starts to dissolve the hydrogen bonds that are within the water. And the reason for that is it disrupts what would be there, because the salt's basically turning the attention from the water itself to the salt, okay? So I like to say that the salt's kind of like, it's all about me, okay? Because the salt needs the hydrogen bonding from water, and it needs those oxygens too to sort of surround it. And so the salt becomes a center of attention, and the water no longer basically gets energy from that process, and it can no longer extend and reach out and touch other water molecules to freeze. Okay, there's ways to calculate this, as in, this is a constant. 1.86 degrees Celsius is how much the freezing point depresses if you have a number of ions or particles in a kilogram of water. Now let's talk about this moles of particles. Last time we talked about equivalence. An equivalence had to do with charge. This is an equivalence. This is how many things are there. So if you have K2SO4, it's going to separate into 2 Ks and 1 SO4. So we don't keep in mind the negative charge. We just say that's 3 things. Okay. If it's NaCl, it would separate it into 2 things, not 3. So that makes a difference. Okay. Boiling point elevation, also same thing. The temperature will go up by a given constant, and that would be given to you, at least for me. Okay. And that is per kilogram of water. So the moles of particles per kilogram of water. Okay, finally, I wanted to talk to you about osmosis. Osmosis is so very important in your body. So you've heard this, getting knowledge through osmosis in your sleep type of joke probably that's out there, but that doesn't really describe what osmosis is. So I want you to consider your cells and the membrane that is in your blood cells. That is what we refer to as a semi-permeable membrane. What that means is water can flow in and out, but other stuff really can't. Okay? So if you have a bit of something inside your cells, say, let's say we've got all kinds of stuff over here, and we only have a little bit of stuff out here, and water is in both, right? The water tends to go towards the area with more stuff, solute, ions, whatever it may be. Okay, so water's going to go in this way. And when water rushes in, that creates a form of pressure. Okay, so this type of concept can be measured and that type of thing, but in general, this happens. So when water comes into the cell like that, because there's more water and less solute out here, and in here there's less water and more solute, then what happens to that cell? It gets bigger, right? Okay, so that is what we call a hypotonic solution. So there's lower solute levels outside the cell than inside the cell. Now when that cell gets bigger, we call that hemolysis. So you're basically making the blood cell larger. It can pop, so you gotta be careful with that. Don't do too much of that. Another form of this would be a hypertonic solution. So in this case, you have a cell with a little bit of stuff, and outside you have a whole bunch of stuff. Okay. Now, when the water goes from where there's less solute to where there's more solute, it's going to come out of solution. Also very dangerous, because then you leave your cells shrunken down and dehydrated. something that we call crenation. So neither of these are really desirable inside your body. Hence why you don't want to drink gallons and gallons of water really fast, and you don't want to eat a whole tray of salt either. So when we get IVs and things like that, we really aim to do an isotonic solution, which means, hey, it's about the same inside the cell as it is outside the cell. Okay. Okay, this can be similar to a dialysis too, just to let you know. Okay, thank you very much.